Is it possible to make forwarding decisions based on something other than IPv4 in an IPv4 network? The answer is absolutely yes. Let's begin. All right, my friend, here are the opt-out questions for this video. So pause the screen, read these 3 questions. If you know the answers to these and are comfortable with those concepts, hey, jump to the next video. I'll see you there. For everybody else, we are going to have a great time right here. Let's begin. I'd like you to imagine in your mind that it's a beautiful Tuesday afternoon. We just had a great lunch, and as we're walking back into our offices, we get stopped by a manager who says, "Do you have a moment? Could you explain to me how IP forwarding works?" And what's our answer going to be? Absolutely yes. We would love to walk you through that process. Probably the first thing we'd want to do is make sure we understand where we're starting with our manager. Now, if our manager already knew about the basic concept of an IP address, that an IP address has 2 components to it. There's a network portion and a host address portion. Starting from there, we could say, you know what? Let's say that this router, R5, has the IP address of 5.5.5.5. Maybe that's a loopback address sitting on R5. And it's been advertised inside of a routing protocol so that the entire network knows how to reach 5.5.5.5. If an administrator sitting at R1 did a ping request over to 5.5.5.5, it would go something like this in an IP network. R1 would consider its routing table, and there is some caching involved with Cisco Express forwarding, and it would determine who should I forward this to. It's like hot potato. How do I get rid of this IP packet destined for 5555? Based on its routing table, it's going to say I need to send this over to R2. In this topology, it's the only path. And R1 could have learned about R2 and R2's willingness to go ahead and forward to R5 through a routing protocol, such as OSPF or ISIS or some other IGP. So the packet, which let's say we're sourcing it from R1's loopback interface, from an IP perspective at layer 3, the packet would be sourced from 1.1.1.1 to 5.5.5.5. That would be the layer 3 header information. So as R1 forwards a frame forwarded to R2, R2 is going to take a look at that data, look at the layer 3 destination address of 5555, and it's going to say, okay, now how do I play this game called hot potato? How do I forward this packet in the right direction? And based on its routing table, which is cached as part of Cisco Express forwarding, it's going to make a forwarding decision, and it's going to forward the packet this way. So it's going to re-encapsulate layer 2 information. In this case, we're on Ethernet with the layer 2 address of R3, but the source address will still be 1.1.1.1, and the destination is 5555. Now, when R3 gets that packet, it's going to look at that destination IP address and say, oh my goodness, what do? It's going to play hot potato. Where do I forward this? And then again, based on its routing table, it's going to make a forwarding decision. It'll re-encapsulate at layer 2 with the correct layer 2 address of R4, which is the next hop. And the packet, if we looked at it right here, would still show source address of 1111, destination address of 5555. And then when R4 gets it and looks at that layer 3 destination address, it has to make a decision. Oh my goodness, what do I do? And then based on its routing table as a foundation for how to forward packets, if it has a route, which hopefully it does, again, based on learning that route through some routing protocol, it would then go ahead and re-encapsulate the packet at layer 2 with the layer 2 address of its next hop, which is R5. And then R5, when he opens that up and starts de-encapsulating and looks at layer 3, R5 is going to say, whoa, that's my IP address. And then he'll continue to de-encapsulate. And if it was a ping request, for example, he would de-encapsulate it up to the ICMP portion. He would see it's an ICMP echo request, and then very likely respond with an ICMP echo reply. In which case, we'd play that IP forwarding game all the way back down. Every router looking for 1.1.1.1, trying to make its forwarding decision. That is traditional IP routing as we know and love it. So if we grab any one of these routers, for example, let's grab R3 for a moment. R3 is just getting packet after packet, analyzing the layer 3 information, and making a forwarding decision based on that layer 3 information. Now, over a decade ago, I mean a long, long time ago, this took a lot of overhead. And you can imagine if you had an old router that was doing routing in software, where it had to think about and process every single one of those packets, the throughput may not be too high, especially if you look more than a decade ago when the hardware wasn't that great. If we had millions and millions of packets, it wouldn't be very efficient. Instead of using the layer 3 IP information to make forwarding decisions, why don't we give the routers something less to think about so they don't have to do all that processing? And that's when they came up with MPLS, multi-protocol label switching. And the key element I want you to take away from this is, instead of forwarding packets based on IP addresses, we're going to have routers forwarding packets based on their labels in those packets. And the reality was, in the past, that by using MPLS forwarding based on labels, instead of doing the layer 3 lookups for IP addresses, we could get a lot more performance in the old days by using labels. Now, the first question is, okay, Keith, where exactly do labels come from? And the answer is, every single router is going to generate a local label for every network they have in their IP routing table. So if we focus, for example, just on one network for a moment, we'll say a 5555/32, that one network address. If we turned on MPLS on these 5 routers, R1, 2, 3, 4, and 5, these routers would generate a local label associated with 5555. And it is all based on the IP routing table. That's how they build their label forwarding information. So let's take R2 as an example. It would say, oh, I have a route from my routing table, IP routing table for 5555. Let me go ahead and assign a label for that. Now the labels, the actual number of the label that R2 can associate with 5555, there's millions and millions of possible numbers that we could choose. We can also limit or constrain the range of label numbers that a router will use. And in this course, I'm going to specifically control the actual range of labels. And the reason for that is for you and I. For example, if we told R2, hey, Mr. R2, whenever you create a new label, use the range of 200 through 299, the benefit of doing that in a training and learning environment is that if we ever see labels in that range, we'll know exactly where they came from. Those were locally sourced labels from R2. Now, the problem with a small range like that in a production environment is if you have thousands of routes, you're going to be expecting thousands of labels, a separate label locally generated for every route that a router has in the routing table. So for this lab environment, I'm going to artificially constrain these to very small numbers. And R3 will be, for example, 300 through 399. And R4 will be 400 through 499. And we'll use that same logic for R1 and R5 as well. Now, not only do these routers generate these local labels, they also will advertise them. And you may or may not be familiar with the concept called the control plane. But the control plane is the mechanism or the avenue in which we train the network on how to reach networks. For example, in IP version 4, an example of a control plane protocol would be OSPF. We're training the network on how to reach networks. Just like OSPF is a control plane protocol for advertising IPv4 information, MPLS also has a control plane protocol. And what we're typically going to use is something called Label Distribution Protocol. And we'll go into the exact details of how it operates and how it negotiates in another video. But for now, I just want you to be aware that once R2 generates these local labels for routes it has in its routing table, it is going to advertise them to its neighbors on both sides. So at the end of the day, R1 knows what R2's labels are for various networks. R2 knows what R3's labels are for various networks. R3 is going to know what R4's local labels are, and so forth. So as an example, let's say that R2, and we're just going to focus on this one route, 5555. Let's say that R2 generated a local label for that network of 203. I'm going to draw an arrow here. 203 references 5555. And R3 generated a local label, as an example, of 303 for that same destination network. So if we start looking at transit traffic again, for example, maybe somebody at R1 doing a ping to 5555, the source IP address would be 1.1.1.1. The destination IP address would be 5.5.5.5. And the layer 2 information, for example, the layer 2 address of R2's interface here, and R2 using the layer 2 address of R3, the layer 2 encapsulation isn't going to change either, because those layer 2 addresses really are going to be the same between R1 and R2 and between R2 and R3, respectively. But what is going to change is we are going to inject, when we're doing MPLS, and I call it layer 2.5, right there. We are going to inject labels into the protocol stack. So what would happen at layer 2.5, as I like to call it, so as R1 prepares to forward a packet to 5555, it's going to know that R2 is its next hop. It's also going to know the label associated with 5555 coming from R2. And what's going to happen is we are going to inject or impose a label. In this case, the packet leaving R1 would have a label of 203, because that's the local label that R2 has associated with that network. Now, at this point, the question is, okay, Keith, great. All I see that happened is we basically added layer 2.5 with an MPLS label to this packet that's being sent to R2. Now, how is that really going to help us? And here's the answer. When R2 receives that data, it's going to de-encapsulate the layer 2 information, and it's going to say, oh my goodness, it's for me. That's my layer 2 address. And then it's going to take a look at the MPLS label, at what I like to call layer 2.5, and as it sees the label of 203, it's going to say, oh, I know exactly what to do with that. It has a label forwarding table that says, oh, if you get a packet that has label 203, go ahead and simply swap out that label with label 303 and forward it to your good buddy R3. And the magic is, and this is important, it never had to look at layer 3 information. It did not have to look at the layer 3 IP address. Now, what does R3 do when it sees this packet come in? Well, it de-encapsulates layer 2, sees its own layer 2 MAC address, processes the frame, looks at the layer 2.5, sees label 303, and it's also going to have forwarding information based on the label distribution protocol. So let's say, for example, that R4 had label 403. So R3 is going to perform something called a swap. It's going to remove the old label 303, it's going to put on the new label 403, and be forwarded over to R4. So as we look at the chain of events here, the packet at point A had a label of 203. The packet at point B is going to have the label of 303. So the old label got removed, the new label got put on, and then once R3 receives it, it's going to take off that old label of 303, put on the new label of 403, and forward it over to R4. And that, my friends, is the essence of multi-protocol label switching. And I want to come back to the point of, okay, so why does this really matter? Again, about a decade or more ago, using label switching was a lot faster than doing an IP lookup at every hop along the path. So a long time ago, it was developed primarily for speed. However, today, in the 21st century, we have some very advanced caching mechanisms, and we have a lot of really powerful hardware-based forwarding that we can use. So MPLS, all by itself, really doesn't give us a bang for the buck. However, there is some magic involved that you definitely want to be aware of, and that's this. Because R2 and R3 and R4 did not have to look at the layer 3 information, my question is, what could we send across an MPLS network if we're not looking at the layer 3 information? So let's say, for example, that this core network that we have is all running IPv4, and we have MPLS added to it. And let's say in our core network we have 250 routers. And then we have a customer who says, you know what, I need IPv6 connectivity between Site 1 and Site 2. Can you help me? Now we have a couple choices. Number one, we could say, well, I guess we could implement IPv6 across every device in our core. Or, check this out, because the core network never had to look at that layer 3 information, we could actually carry IPv6 traffic across an IPv4 network. Because all of these routers, they're simply doing label switching. They're forwarding based on that MPLS label information, and they're not forwarding based on the layer 3 information because they're not even looking at it. We could effectively tunnel lots of different types of traffic across our network. I remember an engineer telling me that MPLS paths, which are also referred to as LSPs, as label switched paths. Label switched paths are so cool because you could actually send water over one. Now that's funny because we can send a lot of amazing things. For example, we could send IPv6 over an IPv4 network that was MPLS enabled. And lots of other protocols as well. Now tangible water is a bit extreme, and that's what makes it funny. Also, because we're doing forwarding based on labels, we can start to leverage those labels in creative ways for things like traffic engineering and quality of service and other really cool features that customers are going to need for their connectivity between Site 1 and Site 2, or for example, between Site 1 and the internet. So to reinforce this, let's have some fun with the wire capture. I have two wire captures I'm going to share with you right here. The first one's called R1 to R2, and that's being taken between R1 and R2 on the wire. And the second one is going to be between R2 and R3. And what we would expect to see is that if R2 had a label for 5.5.5.5, that was label 203, the actual packet sent from R1 to R2 would have that MPLS label injected as part of it. And if R3 had the label of 303 for 5.5.5.5, we should see right here at the second point in the network between R2 and R3, we should see the fact that R2 would have removed his own local label and injected or imposed label 303 before he sent that frame over to R3. So here is one packet of data. If we take a look at the layer 3 information, it's sourced from 1.1.1.1, which is the loopback on R1, over to 5555. So that's the layer 3 information. And the layer 2 information includes the layer 2 MAC addresses. And what I chose to do is hard code the MAC addresses on R1's interface to have a whole bunch of 1s in it, and the MAC address on R2 to have a whole bunch of 2s in it on both sides, and R3 has a whole bunch of 3s, just to make it easier. Also, these captures, in fact, I've got 4 captures, one from point A, B, C, and D. They are all in the Nugget Lab files associated with this video. So if you want to analyze those and take a look at them on your own, they're available for you in the Nugget Lab files. So if this is layer 2 and this is layer 3, then we have layer 2.5, the MPLS header, sitting right here. And you'll notice it's injected label 203, so that's R1 injecting that label as he sends it to R2. We have the MPLS experimental bits, which are for quality of service. And because this was a telnet session, the router I sourced it from automatically set the precedence to 6. And this bit right here called the bottom of label stack simply says that this MPLS label is the last one in this packet, which implies that we could have multiple labels in a single packet. For basic MPLS transport, we only need a single label, but as we will find out together in this course, there are lots of good reasons to have multiple labels for things like traffic engineering and for implementing layer 3 VPN services. And have no fear, you and I will take a look at leveraging an MPLS layer 3 application like layer 3 VPNs that uses multiple labels when we get to that nugget in this course. So if we make a road trip to the packet capture between R2 and R3, which is right here, here we have the layer 2 information with the source and destination layer 2 addresses on this Ethernet segment between R2 and R3. We have the IP header information, which is still sourced from IP address 1111 going to 5555. But if we take a look at layer 2.5, the MPLS label switching header, R2 imposed the label of 303 for the benefit of R3. Now in R2, when it received the label 203 and it took off that label and imposed 303, they call that a swap. We're taking off the label that has significance to us, and we're re-encapsulating the label that has significance for our neighbor. And the cool thing is there's a forwarding table already pre-built that says, hey, you get label 203, re-encapsulate to 303 and forward it. And very similar to how IPv4 caching works with routing information, we're also going to cache that MPLS forwarding information as well, so that router 2 has to spend very little effort to know what to do with a packet that comes in labeled 203. It automatically puts the new label on, forwards it, and says, next packet, please. And one other slight difference here is that in this leg of our journey, the TTL has been decremented inside of the MPLS header. So it came into R2 with a TTL of 255, and we're sending it off to R3 inside the MPLS header with a time to live of 254. And we use that for the same reasons we have it in IP. We don't want a packet to endlessly loop around the network. We need some mechanism to identify that this packet should be killed based on a TTL expiring, and it has that same purpose inside of the MPLS header as we forward traffic through an MPLS network. IP-based forwarding is based on a layer 3 lookup, looking at that destination IP address. While label-based, I'm going to call it 2.5. The industry doesn't officially call it that, but that's a great way to remember where those labels are, stuck and wedged in right between layer 2 and layer 3. The actual MPLS header is 32 bits long, and the actual MPLS label portion, for example, when R1 sent an MPLS labeled packet to R2, the actual number of 203 which it injected or imposed as part of that protocol stack, that's just 20 bits. So what do we do with the other 12 bits? Well, we've got the 3-bit EXP bits, and we're going to traditionally use those bits for quality of service related tasks. So in the trace that we sent, because the telnet automatically marked the IP with IP precedence 6, that got carried over into the layer 2.5 header, the MPLS header, as a 6 as well. And that's why the captures that are in the Nugget Lab files for this video are going to show that those bits, those experimental bits, are set for 110, or in binary, that would be 6. We have a 1-bit representation for bottom of stack. So if you have one label, that will always be set to a 1, that bit, indicating that this label is the very last one. So for example, if we had 2 labels in a protocol stack, the bottom label would have that bottom of stack bit set to 1, and the top label, sometimes called the transit label, would be set to a 0, implying that, hey, I'm not the last label in this stack. And then we have 8 bits for the TTL. And if we add all that up, that it should equal 32 bits for the MPLS header. Now when MPLS is enabled and working, And all these routers know how to forward based on the labels. They have a special term for that path that is going to follow, and that's called an LSP, a label switched path. And routers like R2 and R3 and R4 and R5, who all know how to participate and forward based on labels, we call them LSRs, or label switched routers. And some other terms that aren't too critical right now, but they will be, are CE, PE, and P. And here's what they represent. A PE is an acronym for Provider Edge, meaning this is the edge of our provider network, and it connects off to a customer. The customer's router, in that case, would be the customer edge. So CEs and PEs talk to each other. And a device inside of our core network that doesn't actually have to talk to customers, it's not on the edge, is simply called a P router, short for a provider router. So customer edge is the customer's gear, or at the customer premise. The PE is the service provider, or part of the MPLS network that communicates with that customer edge. And the P routers are simply internal devices, part of the label switch paths that we're building, but not directly interfacing or working with the customer edges. I have had a great time. I'm so glad you joined me for this video. Here's some action items for you right now. I'd like you to take a look at the opt-out questions again at the beginning of this video. And now that we've been through the content together, I want you to make sure that you are comfortable with the answers to those questions to help validate your understanding of the basic concepts that we've learned in this video. Secondly, I'd also like you to take a moment and take a look at the packet capture files, which I've included as part of the Nugget Lab files for this video. Specifically, take a look at the R1 to R2 and the R2 to R3, and as you open those up and look at them in Wireshark, I want you to notice the MPLS header information specifically. What's in there, including that time to live, the experimental bits, the bottom of stack bit, and the actual label information itself, to get really comfortable with what those ingredients are inside of that MPLS header. So again, I've had a great time. I hope this has been informative for you, and I'd like to thank you for viewing.